One of my viewers asked me recently, what is the maximum TX power rating of the loop antenna that I introduced? Today I'm trying to answer this really interesting question. I set up this antenna for different frequency ranges, measured it in detail, and also analyzed it with the program NEC. Ultimately, I was also able to explain the principle of operation, which interestingly is based on both a horizontal and a vertical resonance mode. I will link the videos for you at the top right. Some of my viewers want to build the antenna for their own purpose. In this context, someone recently asked me about the power rating. In other words, what is the maximum transmission power that can be loaded onto the antenna? However, you cannot give a satisfactory answer in one sentence, but I try to answer the question in this short video. For various reasons, you don't want to simply connect the antenna to a transmitter and increase the power until the antenna is destroyed. On the one hand, that would not be legal, and on the other hand, such an attempt would not really be meaningful in general. Instead of this, we better identify the elements that could limit the transmission power of the antenna. By the way, you can apply this method to other types of antennas as well. Basically, like other antennas, this one consists out of a few pieces of conductive material and connection points. The latter, of course, are having a contact resistance, and therefore they can heat up if they are loaded with high current. This effect would destroy the antenna above a certain level of transmission power. The second thing we need to consider is the electric field strength between the elements of the antenna. If the voltage between two elements becomes too high, sparks could jump, causing a temporary short circuit. Okay. Next, let's talk about the method of estimating the maximum currents and maximum voltages on the antenna. Let's assume we feed 100 watts of transmission power into the antenna. With 50 ohms impedance at the connector, this results in an effective current of 1.414 amps. I'm showing the formulas here in case you're not familiar with that calculation. The resulting effective voltage at the feed point would be 70.71 volts, and the maximum peak value of the voltage would be 100 volts. In the case of my example, we can assume that the contact points on the Lustre terminals would bear that current. In addition, the distance between the conductive parts is large enough that a voltage of 100 volts cannot lead to a flashover. Now we need to remember what our antenna matching network is actually doing. You already guessed it. It not only transforms impedances, but also currents and voltages. You can actually see this in the results of the NEC simulations that I performed. The graphic here shows the current distribution on the antenna, and you could derive the exact current values from the numerical results of NEC. But we actually don't need this complex simulation for the following estimation. Let me put it simple. We know that our antenna matching network has a transformation factor of approximately 10. The current distribution along the two-wire waveguide roughly looks like this, and the corresponding voltage distribution is given here. Now we simply use the transformation factor to calculate the value for the actual feed point here at the end of the two-wire line and the current at the short-circuited end. I have to admit that here I'm no longer so sure whether the soldering point can withstand 14.14 amps. Especially when considering the skin effect, causing that the currents are flowing only in the outer micrometers of the conductors. And also the peak voltage of 1000 volts, I wouldn't be so sure that sparks wouldn't jump here in the rain. As you can see, the maximum voltage is getting really high in case a higher power level is applied. But don't worry in case of lower frequencies applying more power. The circumference of the antenna is exactly one wavelength. At lower frequencies, the elements of the antenna are becoming correspondingly larger. Thicker material allows larger contact areas, so the antenna can take higher currents. And the two-wire waveguide for matching becomes also wider, so it can take a higher voltage. So, if you want to drive significantly more than 100 watts, you should use thick material, like copper tube for example. Okay, that was probably more than you wanted to know. But congratulations if you made it up to here. You can also use that method to assess many other antennas, particularly in case you build it yourself. Just as a side note in that context, I reported in a previous video about a 40-meter shortwave antenna that was spectacularly destroyed by high voltage sparks. So you might to leave a like for that video, and maybe you want to subscribe to the channel. Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.